welcome to Zcon4 Day 2. Here we're going to hear from Taylor Hornby about security engineering, Zcash ecosystem security lead. That's right?
Yep.
Okay. Long before computers were invented and security became a widespread problem, safety-critical industries were learning how to prevent catastrophes from occurring. In this talk, Taylor will summarize how he's been working to improve Zcash project security and give an overview of security engineering, drawing insights from safety-critical industries like aviation. These general lessons will be useful to anyone interested in making their projects and teams operate more securely. And with that, go ahead, Taylor.
Awesome, thank you. So this talk is about two things, really. The first part is sort of an overview of the work I've been doing for a Zcash community grant to basically do security audits and stuff for the Zcash ecosystem. And the second part is sort of a general talk about security engineering. Basically, some lessons we can learn from safety engineering that should help you make your software engineering teams able to make more secure software and things like that. So let's start off with the work I've been doing for my grant. So basically, I have this grant that gives me a year of funding to do security audits for all of the Zcash community projects. So I do things like deep dive into the projects, audit all of the code, give them an audit report, and help them fix the bugs. I also have open office hours that anyone can attend just to get whatever kind of security advice they might find helpful. Help respond to bugs that get reported from third-party outside engineers. And I also spend a bit of time thinking about protocol design, like how do we solve the scanning problem in Zcash and get better scalability. What have I done over the past almost year? I've got 2 months left in this grant, and so far I've audited ZecWallet Lite CLI, YWallet, LiteWallet D, Nighthawk's LiteWallet D deployment infrastructure, Free2Z, Zgo, 2 implementations of hardware wallets, both Zondax's and Hans, and I also looked at the zips for Zcash shielded assets. By the way, the time remaining isn't updated, so I'm not sure how much time I have left, but let's keep going. Some other things I've been doing is, thinking a lot about how to solve the scanning problem, investigating bugs, helping with security responses, and probably spending way too much time on the forum talking about the upcoming dev fund and things like that. So here's a summary of sort of my output over the past year in terms of the number of bugs I've found. So a critical bug is drop everything and fix this bug immediately because it's really, really bad. So this would be something like it's possible to steal a user's Zec. That's basically the only thing that would count as critical, and I found 2 of those bugs in community projects. A high severity bug is something that's really, really bad, but not absolutely drop everything and fix this, but still easy to exploit and has really bad consequences for users. So I found 21 of those in community projects. Medium and low are just lesser severity bugs. Low severity bugs are things you can safely ignore, just totally not security related bugs at all. And medium are bugs that could have an impact on users but are kind of hard to exploit, or they really don't have that much of an impact. So 83 bugs in total I found, and 41 of which are medium or worse. So I think that's pretty good. It shows that this kind of security review is effective at plugging the gaps in project security. Now, if we break down the bugs by type, so most of when I look at a project, I'm especially in something related to Zcash, I'm really concerned about the user's funds. So the kind of bug I'm looking for most is what I call a funds at risk bug. And this is a bug that would let an attacker either steal the user's funds or burn the user's funds. So I found 19 of those, and you can see sort of the breakdown of critical, high, medium, and low. based on the colors. Apologies to any colorblind people, because I didn't choose great colors for that. Integrity bugs are like any time an attacker is able to modify some data without permission. Something like changing an entry in a database or something like that when they shouldn't be able to. I found 6 of those. Privacy bugs are basically any time some kind of information gets leaked that shouldn't be leaked. So if an attacker can like read your secret memos that you're sending between your wallets, then that's a privacy bug. Denial of service bugs are like when there's some way to like crash a server or bring a system down so users can't use it. Code execution bugs are your classic like inject SQL code or exploit a buffer overflow to get some code running where it shouldn't be. And then other types of bugs, server configuration. Secure UX is interesting. I focus on that a lot. That means like anytime there's like the user interface of an application is confusing in a way that users are getting less security than they think they are, I actually report that as a security bug, even if there's nothing technically wrong with the software. Because I think like security is really all about like consent and making sure users are aware of the security properties they're getting. So for example, a wallet that uses transparent addresses that doesn't have warnings up that the transparent addresses are private, I consider that to be like a security bug, because people can get confused about that and think transparent transactions are private. So conclusions from my sort of like time reviewing projects for the community. The first conclusion is that like this kind of review is effective. So I found a lot of bugs that shows that like even having just one person who is familiar with the Zcash protocol, just taking really brief looks at these projects, that's effective at finding and fixing a lot of these problems. Most of the bugs I found were like just through a manual source code review, so I didn't use any tooling really. Like sometimes I'd implement a test or like in very rare cases write a fuzzer, but really the most effective thing I found is just like manually looking at the code and thinking about like, hey, what could go wrong here? It's also worth mentioning that I missed some bugs in my review. So I do a review of something and later a bug gets found by someone else. That's always interesting to note because it highlights that security review is never perfect. No matter how much review you have, there are still going to be bugs that are left. But it still is worth doing because you're obviously eliminating the vast majority of them. And the more review you have, the harder and harder it gets to keep finding more bugs. I also found that most of the projects in the ecosystem respond to my bug reports really, really quickly. So a lot of projects would have like patches written within a day, definitely at least within a week. Some projects don't have that though. Some projects are sort of like developers have gone AWOL. It's like people's side projects when they have a full-time job that needs to be their first priority, and they don't really have time to jump in and quickly fix bugs. So one recommendation to the Zcash community I have is to maybe like fund some like bug fix engineers who are just like standing by, waiting for bugs to be found, and then go in and contribute to these community projects. And then I also think that like sort of a better model for this type of work might be to integrate it into the grant process itself. So that with each grant comes an RFP where our auditors can apply to audit the given project. This way I don't have a monopoly over all of the auditing, and it would sort of get some more interest from the security community to start contributing to Zcash. So yeah, that's it for the first part. That's sort of a summary of what I've been doing over the past year. The second part is some general lessons for security engineering. This will be useful if you're at all interested in security and learning how things are secured, especially useful if you are part of a software engineering team or leading a software engineering team to help you get your team up to speed with the best practices. And I'm going to be drawing a lot on safety critical industries. So like industries like aviation, trains, automobiles, things like that. They've been working out their safety story for the past like hundreds of years. And the security engineering community is still kind of catching up to that. So security, especially computer security, is a much newer discipline. So a theme of this talk is that like we can actually learn a lot from looking at safety and bringing over their techniques and stuff to security. So I'm going to start with a few tenets of safety engineering. These are not anything official, but this is just from like reading books about safety engineering. These 3 things stand out as like the key to how we make things safe. And the very first one is learning from failure. So we owe our safety to the people who have died in disasters and to the investigators who work tirelessly to find out why. Anytime you are on a plane or on a train or driving in your car, you are safe because thousands of people have died previously. And people have investigated those incidents, figured out why they happened, and made recommendations and implemented fixes. That's why flying on a plane seems like a ludicrous, dangerous thing, but it's actually one of the safest modes of transportation. So that's tenet number 1, learn from failure. Tenet number 2 is, well, when you think about disasters, you hear a lot about this notion of human error. Like the pilot made a human error and therefore the plane crashed. And what I want to convince you is that human error is really a way of giving up. It's saying, we're going to blame this person. We're going to stop looking for other reasons for why this disaster happened. And we're just going to put all the blame on the person. When actually, if you keep digging, what you'd find is that maybe some equipment was out of maintenance. Maybe the interface that the pilot or whoever was using was very confusing, and it could be simplified and improved. Maybe the person was extremely fatigued because they'd been working for 36 hours straight, and they should have had a mandated rest break or something like that. So that's the second tenet, is anywhere you suspect human error, sort of question that and start to think about, like, how can we make the system more resilient in the face of human error? So this is sort of an alternative to the human error picture called the Swiss cheese model, where basically the holes in the cheese represent things going wrong. And if you get all the way through the cheese, that's a real disaster occurring. So what you want is for your disasters to be blocked at some stage in the process. So an example of this might be an airplane loses an engine, but that's not a problem because it's a multi-engine aircraft and they can fly with one remaining engine. Or in the case of like making it all the way through the cheese, it might be like a driver is driving a car and they mean to press the brake, but they accidentally stomp on the gas. And then they collide with another car because the automatic braking system didn't work. And then they get severely injured because their seatbelt failed. So it took 3 failures. It took the driver pressing on the gas instead of the brake, it took the automatic braking system to fail, and it took some kind of seatbelt failure for the severe injury to happen. So you basically want to make your cheese as thick as possible and have as few holes as possible, which makes the probability of all the holes lining up and an actual disaster happening low. The third tenet for safety engineering is blameless investigation. This is really, really important. This is probably the most important one. So every ICAO disaster report says the sole objective of the investigation and the final report is the prevention of accidents. And that's important. They're not trying to blame people. They're not trying to prosecute people. They're trying to find out why the disaster happened and make recommendations so that it doesn't happen again. Because when you start to blame people, people get defensive, and they're not going to be willing to volunteer information. So yeah, really creating this culture of like blamelessness and just like a focus on something bad happened, let's not blame people, let's learn from it, and let's help stop that from happening again in the future. So that's the third one. So yeah, learn from failure, design for human error, and create a blameless environment. These are the tenets of safety engineering. So this talk is about security engineering from a safety engineering point of view. So I should say something about the difference between safety and security. So safety is really conventionally about like engineers versus nature. So in this picture here, a tank rusted out and ruptured. So that's the engineers battling the forces of rust. Or an airplane, if its engine fails, it's engineers versus the mechanical properties of aluminum or whatever they build engines out of. Whereas security, on the other hand, you're not dealing with a predictable force. Security is really about intelligent agents coming to your system and trying to break it intentionally. They're trying to think of ways to use it that you didn't anticipate, ways to break in, like this picture of a guy breaking down a door here. And safety and security are really sort of becoming the same thing, because obviously if you're not safe, you're not secure. Like a vulnerability in an airplane security system doesn't matter if the airplane's engines always fail and the plane always crashes. Like, so safety is kind of more important than security in a sense. But security is also becoming important for safety as things become more and more connected to the internet. So for example, if your self-driving car can get hacked and be remotely controlled, that becomes a safety risk for the occupants and everyone else on the road. So really these two disciplines are coming together, and we should see in the future more and more ties between these two industries. So let's get to security engineering. So this is like the model that I'm going to present in the rest of the talk. There's this background of culture, and culture is a really important thing in security. Everything I'm going to talk about sort of exists in this background of your organization's security culture. I'm going to say some things that can go wrong with culture and things that you should have in your culture in order to have good security response processes. Another piece is, so this red arrow represents all of the attacks that your system is going to face over its lifetime. The first and the most obvious thing you want to do is like stop those attacks from working. So that's what prevent does. You want to just prevent as many of the attacks from working as possible, but some of them are going to get through. It's impossible to make perfectly secure systems. We just don't know how to do that. Code is too complicated. So the attacks that do get through, you want to be able to detect them, because if you get your system's broken into and the attacker's in there and you never detect them, they have free reign of your computer networks or whatever the case may be forever. And when you do detect them, you need to have an effective response to kick them out. So these are the sort of 3 pillars of security: is first, prevent the attack; 2, detect the attack; and 3, respond to the attack. And then some other useful tools. We talked about learning from failure. A retrospective process is really crucial to have. That's where whenever something goes wrong or whenever you've completed a project, just gather the team and talk about what went well, what didn't go well, and sort of like codify the lessons that you learned from what happened. And obviously another big thing in security is adversarial testing. So this is the audits, the kind of thing I do for the Zcash community. And the idea there is you want to attack your own systems as hard as you can. And the reason for that is the harder you can attack your own systems and the more effort you're putting into finding your own bugs, the harder it's going to be for anyone else to find the bugs, or someone else who has malicious intent to find the bugs. So let's start with talking about culture, because I think that's the most important piece. So here are some hazards that can exist in your organization's culture. The first one is like a blameful environment. So I've already said a lot about this. Sort of a judicial mindset means an environment where you're looking to blame someone. You're looking to like prosecute someone for the bad thing that happened. And that's a really, really bad thing for security and safety, because in that kind of environment, people shut down. Their motive is to defend themselves. They're not going to volunteer information, and it's going to be really, really hard to actually learn from things, because you're not going to get the full picture of what happened. What you want to implement is called a scholarly mindset, and that's where the purpose is to learn, to know the truth, not to judge people, or blame people, or punish people. And if you can foster that kind of an environment, then you really can get at the truth. You can uncover the full spectrum of causes of whatever disaster or incident might have happened, learn from it, and improve your defenses. Another really important thing for teams especially is called an authority gradient. So an authority gradient is basically the perceived level of difference in authority between the team's leadership and the team itself. So if you have a really high authority gradient, like the red smiley face and the blue people with no faces, what happens is people become fearful of speaking up. You have one dictator who's running everything, and they react badly to feedback or anyone bringing up their own ideas, and that creates this environment where if there is a safety risk or if there is a security risk, people are afraid to speak up. On the other hand, if your authority gradient is too flat, there is no clear leadership, then you can end up in chaos. Some cases you might need to carry out a swift action to prevent some security incident or safety incident. And if there's no clear leader, then chaos breaks out and nothing gets done. So you really want to tune the authority gradient in your teams so that there's a clear leader, but everyone still feels comfortable speaking up. Another thing, this is a saying that pilots have, is get-there-itis. This is basically when you've had a long day of flying, you just want to get back to your home airport, sleep in your own bed, and you end up doing risky things to get back because you just want to get there, your mind is focused on, let's just get home, get all of this over with. Yeah, and so this picture here, this guy started flying. He's a VFR pilot, so that means he's currently not allowed to fly in clouds. The weather started to get worse, and he told himself, well, I just really want to get to this other airport. Hopefully it's going to clear up pretty soon. Next thing you know, he's stuck in a cloud, and now this is an emergency situation because he didn't just turn around when the weather started getting bad. So if you find yourself working on a project and you're just trying to get to that deadline, that might be a case of get-there-itis, and maybe that means you should take a pause and just think about, am I rushing this? Should I be slowing down and focusing more on security? Habituation, also known as normalization of deviance, is just the more you do dangerous stuff, the more it starts to feel safe. So if you're working on a roof and you're used to working on roofs without a safety harness, it just becomes normal. You might do it hundreds of times, even thousands of times, until suddenly the one time where you really needed your safety harness and you don't have it. So this is something to be mindful if you have security policies. Just remember that for humans, it's very, very easy to start ignoring them. And ignoring the policy or whatever just becomes normal, and people don't even notice it. So something to be aware of. Task saturation, this is another thing, especially common in aviation, where if you're hyper-focused on one task, or if you have a whole bunch of tasks coming at you at the same time, you basically stop being functional. So maybe this pilot is super focused on programming their map system or whatever, and they're forgetting to fly the plane. So this is especially important for security engineers. If your security engineers or even regular software engineers are overloaded, then they might not be spending the time they need to carefully check for bugs and do their reviews and things like that. Alarm fatigue, as you can see by how annoying this slide is to look at, if alarms keep going off and going off and going off and going off, they start to be ignored. So whenever you have an alarm system, just try to reduce the amount of false positives and try to make every alarm meaningful so that people don't stop paying attention to them. Condition-based maintenance versus periodic maintenance. So condition-based maintenance is like fix it when it breaks. So you keep running the plane until the engine fails in midair, and then it's like, oh shit, we should have fixed that a while ago, or done maintenance a while ago, but now it's time to fix it. In a lot of cases, you really want to do periodic maintenance, which is where your maintenance schedule is based on like frequency. Like you do maintenance every X hours or whatever. That way, your maintenance is way ahead of any possible failures. And this kind of applies to code too, like especially security tech debt. If you're just accumulating and accumulating like weird, buggy, complex code in your software and you're never paying the cost to like refactor it and simplify it and review it, you're going to end up eventually with some big failure that could have been prevented by periodically maintaining it. So those are things that can go wrong with culture. Let's look at some things that can help with culture. So value blamelessness and fallibility. So I'm kind of a broken record on this blamelessness thing. It really is the most important piece that I want to want you to take away. Also, you want to have like a good culture of like just people admitting that they can be wrong, because just like overconfidence and certainty when it isn't warranted is like a great way for security and safety disasters to happen. So yeah, you want to make sure everyone in your team is comfortable saying, I don't know, saying, I made a mistake, things like that. Another thing that you want to implement in your team is a system that I call, hey, that's weird. So this is basically like a group message with everyone in your team where anyone should be able to post like questions about security or like suspicious things that they see. This is good for two reasons. It gives the security engineers the ability to like get a picture of what's going on. So if there really is an attack, it'll show up in here. Someone will be like, hey, I got this like really weird email. It's like demanding a ransom or something like that. And then the security engineer can jump in and help with that. But also there's a second benefit to doing it this way, which is when everyone can sort of see people discussing security, it becomes a shared cultural value, like security matters. And that helps people be less afraid to bring forward stuff. Like if you see like 10 people sharing suspicious things that turn out to be benign, then nobody is going to think, oh, I'm wasting the security engineer's time, kind of thing. So that's a useful tool. A timeout, this is sort of a good antidote to Get-there-itis. So this comes from surgery, actually, where there's these things called wrong site surgeries, or where they will just operate on the totally wrong patient or like amputate the wrong foot, like really, really disastrous stuff. And the way that they fix that and make it less likely to happen is they have a timeout. And what that is where they literally set a timer for like 5 minutes or 10 minutes or whatever, and they just do nothing. That forces them to actually, they don't do nothing. They spend the time like verifying the right patient, right site, all of the details for the surgery. But the timer that they have to wait until that time ends stops them from rushing it. So if you have to wait 10 minutes anyway, there's literally no incentive to rush all your checks. So you might as well take the time to check things properly. So if you feel like you're in a Get-there-itis situation, maybe that's a good time to just say like, hey, we're taking the next 2 days, no work is going to happen, we're just going to evaluate everything that's going on and think about, are we really doing this safely, kind of thing. Another useful concept from aviation is positive transfer of control. So you don't, in an airplane with 2 pilots, you don't want both of them trying to fly the plane at the same time. So they have a protocol where whoever is currently flying will say your aircraft, and then the person who's taking control will say my aircraft. That way, both of them know who is currently in control of the airplane at all times. So this could be useful for like pair programming or any like server administration environment where you don't want people stepping on each other's toes. And then the person who isn't the current pilot flying, they will be the pilot monitoring. So this is like your classic pair programming where the other second person who isn't typing into the text editor is reading what's happening and trying to spot bugs before they get saved. Checklists are another useful thing. You really want to do checklists with two people. You want one person to read the checklist, the other person to execute the item of the checklist, and then say what they just did out loud, and then the first person confirms what just happened. So this like buddy system for checklists makes sure that everything on the checklist is going to happen because two people are looking at the list, and everything gets executed correctly because one person is doing it and one person is verifying it. With checklists, though, you want to beware of rhyming the lists. So this is some random aviation checklist. So in the cockpit, it would sound like auxiliary fuel pump off, flight controls free and correct, instrument and radios checked and set. And you can kind of see how if you've done this hundreds of times, you'd start to just automatically say off or checked and set after you hear the cue of the checklist. And a defense against that is pointing and calling. So this is what Japanese train operators do. They will literally point at their speed when they're making some change to their speed, or if there's like a signal out the window, they will point and they will say out loud what the state of the signal is. And so that sort of involvement with your body and your language is a defense against becoming complacent and making mistakes where you're just not paying attention, kind of thing. Okay, so summary of the culture. I'm not going to read all these again, but just basically avoid blameful environments. That's the most important thing. Keep in mind all of these things like Get-there-itis. Check out your authority gradient. You want to have a healthy authority gradient, not one that's too steep or too flat. Beware of Get-there-itis, task saturation, things like that. Use tools like, hey, that's weird, timeouts, and checklists to make sure you're doing all the right things. So now let's look at these three components of security: the prevention, detection, and response. So the first step to preventing security threats is a threat model. And there's two major ways of doing this. The first and like pretty common way is to like enumerate all the possible ways your system can get attacked. That's like really complicated and really technical because you kind of need to be a security engineer to like even think about all the possible attacks. A better way to do it is to instead describe what users expect of your system in language that they understand. So someone using Signal might say, I expect that nobody except me and my friend can read our encrypted messages unless someone breaks into one of our phones. So that's something a user understands, a security engineer understands, and you can build a threat model by making up a list of claims like this. And then in that case, a bug is anytime one of those expectations are violated, but also anytime a user has an expectation that isn't on your threat model list. So if a user is assuming Zcash transparent addresses are private, and they're actually not, that's a security bug, even though the software is flawless. So a bunch of random things to sort of prevent security bugs. This could be a whole talk in itself of like what to implement in your organization. But just like quickly, the most important things are like get everyone on a password manager. That will stop phishing attacks because the password manager is making sure the password is only going into the legit site and passwords aren't being reused. Use two-factor authentication. It's quick to set up, so do it. Make sure you have security support available for your organization. Everyone should know who to talk to if they suspect some kind of attack. And we just talked a lot about culture. Make sure you implement those cultural tools and avoid those cultural hazards in your organization. If you're a coder, Use memory-safe languages, so choose Rust over C and C++, because it's just not possible to write secure code in memory-unsafe languages, in my opinion. Use parameterized queries, so you're just completely eliminating SQL injection vulnerabilities. Write unit tests, make sure code gets reviewed by at least one other person, and implement audits. And then DevOps stuff, yeah, DevOps server deployment stuff, yeah, just make sure everything's up to date. Make sure access is limited so that even your own employees can't access information, and just avoid storing data that you don't need to store, because like data that doesn't exist isn't at risk of being stolen. So that's prevention. And about detection, I'll just say machines get malware, networks get breached, bugs get exploited, accounts get hacked, and data gets leaked. And that's no matter how good your prevention is, no matter how much you've audited your code, set up your servers correctly, or whatever, attackers are going to get through. So you have to have some kind of detection methodology in place. That could look like intrusion detection on your endpoints, or like logging and people reviewing the logs, or like some kind of AI-based system, or whatever you want. This is probably the hardest piece to actually get right. You also need to respond to security incidents quickly and effectively. So you want to have clear severity rankings for incidents. You want to know if an incident is like, drop everything, we need to work on this now. Like someone just stole our like hardware wallet seed phrase or something. We need to move the funds now. Or if it's like more relaxed, like we got to fix this in the next like sprint or so. Make sure you have clear roles in your response process, like know who is going to investigate the issue, who is going to decide which actions to take, who is going to communicate to the public, and things like that. And you also want to like practice this. Usually you just have enough security incidents on your own that you don't really need extra practice, but if you don't, then just do a run-through of the process, just so it's familiar to everyone. Okay, so we've looked at the culture, we've looked at prevention, detection, and response. The next big piece of any security process is the retrospective. So the retrospective is learning from the failure. This is like one of the most important pieces. Basically, when you have a security bug, you want to collect all the relevant technical information, get everyone into a meeting, let everyone discuss what went well, what didn't go well, and go around the room and just record all the ideas people have, write everything down, and then decide on some action items, like what did we learn from this incident, what should we have done to prevent this, document it all, and then in a couple weeks, have someone give a brief to the company or like the wider organization on what they learned, and then like far down the line, review it again so it doesn't get forgotten. Let's skip over this. So one thing to be wary of when you're doing a retrospective is root cause seduction. So for example, a plane might crash because the engine quit, and you might think like, oh, the problem is that the engine quit. So you do a deep dive into how exactly the engine failed, and you make recommendations that fix the engine and make them less likely to fail. When actually there's a whole bunch of other factors that contributed. Like maybe the pilot didn't give themselves enough altitude to let them make it to the next airport, or maybe the pilot's like training of engine failure scenarios wasn't adequate or something like that. So if you find yourself focusing on like one obvious cause, try to like broaden your perspective and think about like what else could have prevented this whatever bad thing from happening. So yeah, you want to make sure you document the outcome of your retrospective. If you just do a retrospective and you don't do anything with it, then it's just going to get forgotten, and only the people who were in the retrospective will remember, but probably not. So give like the wider organization a brief in a couple weeks' time, and then just review it again, like after 3 or 6 months. The repetition will get things saved in people's memory a bit better. So the last important piece of security engineering is adversarial testing. So this is like audits. And so the thing to remember here is that you have bugs. So when I approach a project to audit, I never, ever, ever let myself become convinced that it doesn't have a bug. Because as soon as I let myself even consider that, I lose the motivation to try to find bugs. So every piece of software has a bug, you just haven't found it yet. That's the mindset to be in when you're an auditor. Yeah, and so basically the way this works is there's like two components. The first component is you're trying to find bugs before the actual attackers do. Because if you can find it first, you can fix it before it gets exploited. And the bugs you find are also telling you about how your engineering practices are failing. So it tells you that maybe you're not doing enough code review, maybe your code review isn't looking for the right things, or something like that. So investing in discovering your own bugs both fixes those bugs and helps you improve your overall process. So if you want to be an auditor, what you want to do is cultivate what's called the adversarial mindset. This is basically learning how to think of things in how should I say it? You want to look at things as they really are rather than as they were intended to be. And just sort of think of like ways to break things and ways to use things in ways that they weren't intended to be used. And if you sort of like practice doing that in your daily life, you sort of start to see things differently. Like, I don't have a good example off the top of my head, but yeah, so next time you're going through like a security checkpoint or something like that, like just be creative and fun and like think about like, oh, how would I get something past this? What could I do? And here's like an example of some code. If there's any like coders in the audience, they want some experience finding a bug. Here's a function that transfers some money from one account to another. So it checks if the from account has enough balance. And if it does, it adds that amount to the to account and subtracts it from the from account. And there's a bug in here that will let you get free money if this code was ever used in a financial application. So you can also look at the slides later to look at that if you want. So my process for security audits is basically it's just like a creative process. Like you learn about the system that you're auditing, make a bunch of guesses about what could be wrong with it, carefully review all of the code, and you end up with this like brainstorm of like a bunch of things that could possibly be wrong with it. Once you have that, go through and like carefully confirm the issues, understand how bad they are, what are the risks to users, and write up a report. So audits can be done internally and externally. So an internal audit is when your own engineers do a security audit of your software. And that's good because your own engineers are the most familiar with the code, obviously, because they're working on it every day. And it also helps to develop an adversarial mindset in-house. So even your regular engineers can participate in an audit, not just your security engineers. And that'll help them get thinking about like, what could go wrong with my code, and sort of like help them integrate that adversarial thinking into their regular development. An external audit is when someone outside of your organization comes in, audits your code. And that's not just useful because they're professional auditors, that's useful because they're seeing your code with fresh eyes. So they don't have all of the entrenched assumptions that your engineers have when they're reading the code, because they're literally seeing it for the first time, struggling to understand it. And in that kind of an environment, it's more likely for bugs to be found. Okay, so I have a bit of time, so I'll talk about some of the bugs I found before wrapping up. One of the bugs I found, so in the spirit of blamelessness, I'm going to leave off all the names of the projects. These are all Zcash community projects, but I'm going to leave off their names because the point here isn't to blame any developer for the bug. The point is to look at these bugs and learn from them. So I picked a few bugs that I think are sort of like unique to Zcash. They're not like your standard type of security bug that I think we can learn from. So in this case, a wallet used the Zcash memo field to store a contact list. So literally, the wallet would send itself a memo, and it would say, like, Bob's address is whatever. And then when the wallet would sync, it would receive all its memos, and it would recover the contact list by looking for any memos that were formatted that way. The bug in this is that anyone can send the wallet a memo that's formatted that way. So the attacker tells Alice's wallet, Bob's address is my attacker's address, and the attacker tells Bob's wallet, Alice's address is my attacker address. And now when Bob and Alice are using their contact list to communicate with each other, all of their messages are actually going through the attacker. So the attacker can read their conversation. Another bug is another wallet would automatically auto-shield your transparent Zec. So whenever the user made a shielded transaction, it would look and see, do I have any transparent balance? And if it does have transparent balance, it will include a transparent transaction in the shielded transaction that you're making that moves the transparent funds into your shielded wallet. And that's a privacy bug, because what an attacker can do, if they know your transparent address, it just makes sure there's always balance in there. And then whenever the user creates a shielded transaction, the wallet's always going to do this auto-shielding. So every shielded transaction that they make will include this transparent component, and then the attacker can just look on the blockchain and see which wallet created all of the transactions, because they see all the transparent parts. Another neat bug was a payment processing service let you pay for orders by actually sending the money to yourself, so you could get things for free. And that's because the way it processed orders, it would look at all of its customers' addresses, all of the memos sent to those addresses, and find the order IDs in the memos. And it would check, is the payment enough to pay the order? And if so, it'd mark the order as paid. But there's a subtle bug in this, which is that it's not actually making sure that the payment is going to the correct address. So a store creates an address and they expect the payment to go there, but what an attacker can do is they can actually sign up for this payment processing service and register their own address, and then when they go to pay an order where the money should go to someone else, they actually send their own address the money with the correct order ID in the memo. And then so the payment processing service would tell the other person, hey, the order's been paid, but the attacker would still actually have the money. I also found a bug in a hardware wallet. So the way the hardware wallet works is like sort of the host computer that's like your smartphone, or the computer that's talking to the hardware wallet, goes through this process of adding transaction components. So it adds the transparent inputs, outputs, sapling outputs, orchard actions and stuff, and sort of like each time it goes to the next stage of the process, it calls this change stage function to tell the hardware wallet, hey, I'm done with this stage, I'm ready to start adding the next components to the transaction. And so the bug in this wallet was, so here's the change stage function. What it does is it makes sure that you're only changing to the next stage. So you don't want to let the host change to an arbitrary stage. That'd be bad. You want to do these in order. And then it has a switch statement that processes the different state transitions. But what was missing here was a default case in the switch statement. So if, in particular, it didn't have handlers to make sure that you're actually doing the state transition properly. So in this particular wallet, when you get to the stage fee, what should happen is once you're in fee, that lets you call the thing to display the fee confirmation to the user. And then the user has the option to like confirm or deny. And only if they confirm, the stage should go into sign. Sign means it's okay to start signing the transaction, producing those signatures. So the bug was you could make a transaction that spends all of the user's funds into the fee, get it into stage fee, and show the fee confirmation. But then when the user is looking at the fee, you call this change stage again with stage fee +1, which happens to be sign, and change the state into sign without actually having the user confirm the fee. So it was possible to basically burn all of the user's funds into the fee. Or if you're working with a miner, you could collaborate to steal the user's funds. So yeah, that's it. So just to wrap up, the tenets of security engineering that we've learned from safety engineering are, one, learn from failure. Yeah, the way that safety and security are created are from learning from our mistakes. Design for human error. So remember that like assigning human error to something is really a cop-out. It's saying like, I'm not willing to look further. I'm not willing to make systems better to compensate for mistakes humans make. Create a blameless environment that helps you find the truth. Make sure you have all of the information available to you for making things more secure. Prevent, detect, and respond. So prevent bugs as best as you can. Know that attacks will get through anyways, so you need to detect them, and have a system for responding to attacks when they happen. And finally, attack your own systems. You want to find those bugs before the attackers do. And yeah, so that's the basics of security engineering, and if you follow these things, you should be well on your way to preventing most attacks. And that's it. Thank you.
All right. We've got just a few minutes for some questions. The privacy guarantees of Zcash must be based on rigid security practices. Has your time in the Zcash community affected your own research and auditing engineering practices?
Yeah, in a couple ways. So I think, number one, I got a lot more experience auditing from the Zcash community, especially like this grant that I'm working on. It's just a lot more auditing than I've done before. So I think I've like leveled up a bit there. But also like just working at ECC and working with like the amazing engineers at ECC taught me a lot about cryptographic engineering. Like the kind of cryptography in zero knowledge proofs was like at one point just like totally incomprehensible to me, and I'm like starting to make my way towards understanding it. So yeah, it's really just like learning from other people in the community is the biggest thing.
How do we stop burnout among security engineers?
Ooh, that's a good question. I think one of the leading causes of burnout for security engineers is they can get put in a situation where they feel like they're the like first line of defense against attacks, and that's a lot of pressure, right? Like if you fail, like users are going to be harmed by attackers, and so I think the way to prevent burnout is like really don't overload them. Make sure there's like a lot of space, because it's like really security work is really emotionally taxing. So make sure there's a lot of like space to take time off, and also make sure that like leadership of the organization is like really listening to them and offering help, like so that like if you're working as a security engineer and there's like an engineering component to the organization, the security people should be able to like allocate some tasks to the regular engineers to like sort of take a load off.
When designing for defense in depth Swiss cheese model, how do we balance layers, thickness with performance, efficiency, code bloat?
That's tough. It depends on the specific application. But I would say it really comes down to learning from failures. So look at what has failed in the past and beef up the things that are failing. Yeah, I don't really have a better answer. But good question.
Manual code review seems hard to scale up. How can we grow the number of engineers who can do these kinds of reviews?
Yeah, so that's really important. I think this is the one thing that like the world needs to actually achieve security, is like to realize that we can't just like encode this process into a tool. It really can't be automated, because like the process real attackers are using to find bugs in your system they're using all of their intelligence to be able to do it. So I think we need to create a pipeline where we're like teaching this stuff and giving like regular engineers and new graduates training and like space to just have fun, like trying to find bugs, and like some kind of like mentorship program to like just have like a huge pipeline of like people learning this stuff, because yeah, we really do need like a lot of people who are good at this.
It's good to see us catching severe bugs in production code before they impact users. How can we prevent these bugs earlier, for example, at the protocol design?
Like auditing early is a really good thing to do, but also consider the like secure usability of the protocol. So if you have a protocol that you're noticing is consistently being used in an insecure way, or a library that's consistently being used in an insecure way, that should actually clue you in that it's a problem with the protocol itself or a problem with the library's API. And you shouldn't like expect the developer to know about all these pitfalls. You should actually fix the library's API to sort of rule out those problems.
Okay, that's actually all the questions we have. There you go, Michelle.
Thank you. When you go back to some of the grantees with your feedback, your findings, like what kind of responses have you received? Do you find that they're all very receptive, or like some defensiveness?
So outside of, like in my work before Zcash, I would get a lot of defensiveness when I would just volunteer and audit stuff. But within the Zcash community, everyone has been supportive. Like nobody's been like nobody's gotten mad at me for pointing out flaws or anything like that. It's all like, oh wow, thank you. Like they really see it as like a free resource that they're getting, so they're appreciative.
Taylor Hornby, thank you so much. That was extremely informative.
Cool, thanks for listening.